Good morning and good afternoon, everyone. I'm Sita and Shah. My meeting number is 2223001, and I'm the lead system architecture and the project manager for this project. Today, I will present about our system, which demonstrate a digital communication link using a multi-site coding, BFSK modulation, and noise simulation with AWG and EPAD. So, I'm going to explain about our block diagram. So, first, the system flow start with the input data being passed into the Manchester encoder. So after encoding, the signal is passed into the BFSK modulation module where digital bits are converted into the frequency signal. The modulated signal is then transmitted through the communication channel, which include a noise simulation using a potentiometer. So finally, the receiver decode the signal and check the integrity using the SO checksum and display the result using the LED and OLED display. So this entire system is implemented and tested using the Walkway ESP32 simulation platform. So this project is a collaborative effort where each member contribute a specific module. That's all for me.
Hi, I'm Ada. I'm a baseband coding engineer, and I will present about the Manchester logic. Here is our Manchester encoding. So Manchester encoding converts into each binary bits into the pair of bits, which is if the binary 1, it will convert into 1 0. If the binary 0, it will convert into 0 1. And for the Manchester decoded here, it will reverse the process, which is 1 0 into 1, 0 1 into 0. That's all.
So now I'll be presenting my part. So Assalamualaikum and hi everyone. My name is Ahmad bin Azmi and my metric number is 224411, and in this project I am the bandpass modulation engineer. So my main responsibility is translating our encoded digital bits into physical frequencies using BFSK. So by looking at the send bit function as shown here, so the process starts by determining the target frequency. So using a ternary operator, the system assigns either frequency 1, which we set to 3500 Hz, or frequency 0 set to 1100 Hz, depending on the incoming bits. So the microcontroller then executes this by setting the transmission pin high, pausing for the calculated microsecond delay, pulling it low, and pausing again. So this continuous toggling physically generates the square wave you can see on channel D or of the logic analyzer. Can you show the logic analyzer, Nadia? Okay, thank you. So when you look at the waveform, the logic ones are represented by dense, rapid pulses because the calculated delay is very short, around 142 microseconds, while the logic zeros appear as wider pulses because the delay is much longer, which is around 454 microseconds. And finally, we also implemented a noise parameter by artificially adding extra microseconds to delay t based on the potentiometer input. We simulate AWGN or additive white Gaussian noise, which stretches the waveform, distorts the timing, and allows us to stress test the receiver. That is all from me. Thank you.
So I'll be continuing. I am Muhammad Karis bin Muhammad 224208, and I am the checksum UI of the Walkway simulator. And basically my purpose is to do an error detection of our logic. So we're using an XOR checksum which implemented to verify the data integrity after the reception. So we are assigned for a nibble of a bit of 1110, and then the checksum bit is generated by performing an XOR operation of our 4 bits. Thus showing on our left screen is our coding to calculate of our checksum, and then we'll be continuing on our Walkway simulator. If the checksum, if the potentiometer is under 299 according to our calculation, it will receive the data of 1110, and then the checksum will indicate a green LED to indicate the bits, and then the yellow, and then it will show a pass sign. So if we increase the potentiometer to more than 299 microsecond, it will show us a status of a fail, and it will read the data of 1111, and a red LED will light up to indicate the fail status. That's all from me. Thank you.
Hi, my name is Vanakimla binti Muhammad Razaini, and my matrix number is 224493. And I, as an investigation and a QA lead for AWGS stress test. A potentiometer was used to simulate increasing channel noise, representing the effect of additive white Gaussian noise on the communication link. During the testing, the potentiometer was adjusted gradually to increase the noise level while monitoring the transmitted and received data. At low noise, at low noise levels, the transmitted data 1110 was received correctly and the checksum verification passed successfully. However, when the noise reached approximately 298.7 microseconds, the system reached its failure point. The received data changed from 1110 to 1111 due to transmission corruption. As a result, the calculated checksum no longer matched the received checksum, causing the checksum test to fail. When fail occurred, the red LED turned on as a visual error indicator, and the OLED display showed fail to indicate an unsuccessful communication. Thank you.
So in conclusion, our system is successfully demonstrate a full digital communication pipeline using a transmission to reception. It includes message encoding, BFSK modulation, SO checksum verification, and AWGN noise simulation. This allows us to analyze how noise affect communication really in real world scenario. So that's all for me. Thank you.